Nanoparticles are tiny materials with dimensions typically ranging from 1 to 100 nanometers, nm, in at least one direction. Due to their extremely small size, they often exhibit unique physical, chemical, and biological properties that differ significantly from their bulk material counterparts. These novel properties make them highly valuable in a wide range of applications. Structure of nanoparticles. The structure of nanoparticles can vary greatly depending on their composition and synthesis method, but generally, they consist of three main parts. Core. This is the innermost part of the nanoparticle, typically made of the primary material, for example, metal, semiconductor, polymer. Shell, optional. Some nanoparticles have a shell layer that surrounds the core. This shell can be made of a different material, often used to modify the nanoparticle's properties, for example, improve stability, control release, add targeting capabilities. This is known as a core shell structure. Surface layer, the outermost layer, which interacts directly with the surrounding environment. This layer can be functionalized with various molecules, for example, surfactants, polymers, ligands, to enhance stability, solubility, or to enable specific interactions. For example, targeting specific cells in biomedical applications. Nanoparticles can also have various shapes including spherical, rod-like, hexagonal, cubic, cylindrical, or irregular, and their internal structure can be crystalline or amorphous. Composition of nanoparticles. Nanoparticles can be composed of almost any solid or liquid material. Based on their chemical composition, they are broadly categorized into organic nanomaterials. These are synthesized from organic molecules, often polymers or lipids. Examples include liposomes, spherical vesicles made of lipid bilayers, often used for drug delivery. Micelles, aggregates of surfactant molecules, also used in drug delivery. Dendrimers, highly branched, tree-like polymeric structures with precise molecular weights and shapes. Polymeric nanoparticles, solid particles made from polymers capable of encapsulating drugs or other active agents. Inorganic nanomaterials. These typically consist of metals, metal oxides, or ceramics. Examples include metal nanoparticles, such as gold, AuNPs, silver, AgNPs, iron, FeNPs, copper, QNPs, and platinum, PTNPs. These are widely studied for their optical, electrical, and catalytic properties. Metal oxide nanoparticles, including iron oxide, for example, Fe2O3, Fe3O4, titanium dioxide, TiO2, zinc oxide, ZNO, aluminum oxide, Al2O3, and silicon dioxide, SiO2. They often exhibit unique magnetic, catalytic, or UV blocking properties. Quantum dots, QDs, semiconductor nanocrystals that emit light of specific colors depending on their size, due to quantum confinement effects. Carbon-based nanomaterials. These are composed primarily of carbon atoms arranged in various structures. Examples include fullerenes, spherical or ellipsoidal molecules of carbon atoms, such as the buckyball, C60. Carbon nanotubes, CNTs. Cylindrical nanostructures of rolled-up graphene sheets, known for exceptional mechanical, electrical, and thermal properties. Graphene, a single layer of carbon atoms arranged in a 2D honeycomb lattice, with extraordinary strength and conductivity. Carbon nanofibers, filamentous carbon structures with stacked graphene layers. Composites, materials that combine nanoparticles with other nanoparticles or with larger, bulkier materials to create new types of nanoparticles. Nanoparticles can also be classified by their dimensions: 0-dimensional, 0D, nanomaterials. All three dimensions are within the nanoscale, 1 to 100 nanometers. Examples include quantum dots and spherical nanoparticles like fullerenes. 1-dimensional, 1D nanomaterials. 2 dimensions are within the nanoscale and 1 dimension is larger. Examples include nanotubes, nanowires, and nanorods. 2-dimensional, 2D nanomaterials. 1 dimension is within the nanoscale and 2 dimensions are larger. Examples include nanofilms, nanolayers, nanocoatings, and graphene sheets. 3-dimensional, 3D nanomaterials. These are bulk materials where nanoparticles are dispersed, for example nanocomposites, or where the nanoscale features are aggregated, for example powders of nanoparticles. Functions of nanoparticles. The unique properties of nanoparticles, primarily their high surface area to volume ratio and quantum confinement effects, enable a wide range of functions and applications. Enhanced reactivity and catalysis. The large surface area provides more active sites for chemical reactions, making them excellent catalysts in various industrial processes. For instance, metal nanoparticles are used in chemical synthesis and environmental remediation. Optical properties. Nanoparticles can interact with light in unique ways. For example, plasmonic effects in gold and silver nanoparticles allow for strong absorption and scattering of light at specific wavelengths, used in sensors, imaging, and photothermal therapies. Quantum dots emit specific colors of light when exposed to UV light, useful in LED displays, biological imaging, and solar cells. Electrical conductivity. Carbon nanotubes and graphene exhibit exceptional electrical conductivity, making them suitable for advanced electronics, flexible devices, and energy storage, batteries and supercapacitors. Magnetic properties. Magnetic nanoparticles, for example iron oxide, display superparamagnetism, which means they can be manipulated by external magnetic fields without retaining magnetism after the field is removed. This property is vital for MRI contrast agents, magnetic separation, and targeted drug delivery with magnetic guidance. Drug delivery and biomedical applications. Targeted delivery. Nanoparticles can be functionalized to recognize and bind to specific cells, for example, cancer cells, delivering therapeutic agents directly to the disease site, thus minimizing side effects on healthy tissues. Improve bioavailability. They can encapsulate drugs, protecting them from degradation, and improving their solubility and absorption in the body. Imaging and diagnostics. Used as contrast agents in MRI, kinetic, and optical imaging, or as fluorescent labels for biological sensing and diagnostics. Therapeutics. Beyond drug delivery, some nanoparticles themselves have therapeutic properties, such as the antimicrobial action of silver nanoparticles or the photothermal capabilities of gold nanoparticles to destroy cancer cells. Material enhancement. Incorporated into existing materials, for example polymers, ceramics, to improve mechanical strength, durability, scratch resistance, and flame retardancy. Examples include stronger plastics, crack-resistant paints, and self-cleaning surfaces. Environmental applications, used in water purification to remove pollutants, in catalysts for reducing emissions, and in sensors for detecting environmental contaminants. Energy applications, employed in solar cells to improve light absorption, in fuel cells for efficient energy conversion, and in batteries for